called thinking critically.
Yeah, I dropped this last time.
It was not amazing. Did you share your screen?
What do you have to read?
I'm just going to do a paper on the axiology of science. It's like about the determination of what is scientific value. Determination of scientific value.
Yeah, nice.
Okay, so welcome to the second to the second day of the new era of solar physics, I guess. So I hope you all see these amazing images from yesterday, and also for these who didn't hear, Eugene Parker got the Crawford Prize, which is like a compliment to the Nobel Prize, if I understand properly. So that's another justification that solar physics can also be fancy and prestigious, like the other astrophysical disciplines do.
So, a Nobel Prize that doesn't exclude solar physics.
Yeah, exactly. That's like
a Nobel Prize that doesn't exclude solar physics.
Well, what kind of solar physics things should have gotten a Nobel Prize?
Yeah. Okay, well anyway, in the last class we have seen what happens when we try to remove the effects of the Earth's atmosphere. And Kevin is going to continue today, and he's going to tell us something about some other methods, and probably actually show us how are these applied, maybe even in the data that we saw yesterday. So everybody enjoy.
Eglin, Leo.
Oh, okay, Eglin, yes. Yeah, you know, they go into the physics and
yeah, you're
the
competing in the 40s
with
the quantum,
the neutrino thing, then it became a physics thing. So, yeah, like spectroscopy.
So yeah, no Nobel Prize work in today's lecture. All the rudimentary nuts and bolts grinding away to make our images.
To get the New York Times cover.
To get the New York Times, the cover of the New York Times. What do you have to do? So just, I wanted to go back and looking at a lot of things about turbulence. We talked about this some, but as different things come up, it's good to have this schematic picture of what the atmosphere is doing. So we have these plane waves coming from the sun. They run into these turbulent pockets in our atmosphere that have different temperatures. That creates a different index of refraction, which ends up distorting the wavefront that we get. So that would be, you could deal with that easily enough, perhaps. But there's our aperture where we measure that distorted wavefront. But the problem is, one, we don't have a single layer of turbulence, and it's not so easy. We have these several different layers, a high altitude layer where the jet stream is often, and a ground layer. And both of those actually change with time. So that high altitude layer where the jet stream is being pushed by the wind, so these things are moving rapidly across our line of sight. And then at the local level, we have all the ground heating and the telescope that's producing these time-varying atmospheric distortions as well. So that's why we run into this problem that our MTF is now, as we saw, is changing with time, right? It's no longer a constant MTF, but it's very rapidly changing. So how can we figure out what that is? In nighttime, they have this nice feature that they have point sources, and they have stars that they can look at, and a star, a point source should be a point source, and so you can determine the PSF directly by looking at those. We don't have those. We did see that with those Hinode things last week, you can use sort of known structures, known intensity structures in your image, such as the lunar limb or a planet transiting, and you would get, that would tell you what your PSF is. You can fit that to get your PSF. Unfortunately, those kind of things happen very rarely, so we can't use them on a regular basis. From the adaptive optics, we're measuring what those wavefront errors are, and so we can determine what the point spread function is, what the MTF is from the adaptive optics. That is done, but it has been done, but it takes a lot of data, right? AO is running at a couple thousand hertz, measuring a bunch of apertures, and you would have to calculate all those the distortions afterwards. maintain all that data and calculate it, and then that would only give you the PSF at one point in your field of view where the AO is locked on. And we'll see we want to get this across the whole field of view. And then last week we talked a little bit about these blind deconvolution techniques, and today we'll go on and talk about speckle reconstruction. And so these last two are what are primarily used to get to figure out what the MTF is and reconstruct our image, get back, try to find the original object that we're observing on the sun. So that's all talking about what the seeing is. What does it really look like? What does the sun look like when you're observing it from the ground? So this is one time series sampled. This one's sampled at about 6 or 7 hertz. And so the playback will be twice, it'll be about 15 frames per second. So about twice what the true seeing is. Hold on, go back. That started. And so yeah, this is, it's a little jumpy here, certainly over Zoom. You probably want to download the PowerPoint and see it locally. But what you can see is that the seeing is changing over the whole field of view on a from image to image. There's a lot of significant changes. There's some jumps in there. And so you have some good images at different times in the sequence, a nice sharp image, and a few seconds later, things have gotten, the PSF has gotten much worse. You actually can look at this, we're even at 7 frames a second, we're not in any way resolving what's going on with the seeing. So this is another data set. It's taken a little higher resolution. So this is the average over the entire sequence, and you see it's.
What do you mean higher resolution?
Higher spatial resolution.
Smaller scale.
Smaller scale.
Pixel size.
More pixels. The granules you see are a little bigger here.
Oh, okay, that sense.
So there the granules use a lot. So the image is the same size on the screen, but it's sort of zoomed in. But what's nice here is this data set covers only 2 seconds. We're running the camera at 400 hertz. So now we have an image every 2.5 milliseconds. And so now we can actually, in the movie, we can actually see the seeing vary and slowly evolve. And we see areas, where you have it sharp for a second, and you can see it then slowly blur out. If you analyze this, you can actually see those seeing patterns moving across the image, where one bubble of the atmosphere is moving across the aperture, and you see it affecting different parts of the field of view.
How long is the sequence again?
The whole sequence is, as taken, was 2 seconds. 2 seconds. And it's played here 10 times faster than that.
Slower.
10 times slower, yes. Right.
So in 2 seconds, you see the pattern?
Yes.
Wow. Okay. And that is what, 50 of seconds, 30 of seconds?
Something like that. Wow. So here you can actually, start to see what's going on, what we're fighting against down in the. So even looking at this, the correlation from one frame to the next, it falls off quickly. So things are varying rapidly. So now how we deal with this again? Now we'll go back and figure out how to fight this fight. So we saw this blind deconvolution last week. We get these multiple realizations now. We take multiple images, and what that gives us is what's called diversity. We have different realizations of that top combination of my object and my MTF. That allows me to try to solve that as a sort of a system of equations and do a minimization to find an optimal solution for that I0, my original object. I had this PSF, and I'm really trying to find the aperture itself is fixed, obviously, over the course of the observations, but it's my phases that are varying. And I want to find, try to fit those phases with a series of functions. These polynomials, the Zernicke polynomials is one. There's different kinds of polynomials, and find the coefficients. And so those alphas for each of the different polynomials. And I'd like to fit as many as possible to get the the phases across the aperture are going to be rather have power in different spatial frequencies on the aperture, so I want to fit as many of these as I can, but still get a reliable fit. So these were these Zernike polynomials last week. Someone asked, where did this come from? It actually came from a paper about identifying using the Zernike polynomials and another basis set to try to identify the vanilla bean flower and figure out what the how to identify this flower so they could help them with the manual pollination of the vanilla bean. So you find these things pop up all over the place, in the strangest place. But in optics, they're heavily used, of course. So the first 6 modes are sort of the classic, the sort of minimal set of modes in some sense to define some kind of optical aberrations. You can go up higher and use all 36 of these modes. But of course, this is just a continuous series, a higher and higher order. So you can go up to hundreds of modes. So I'm going to show you a series of reconstructions with the MUMP-BD or the MFBD, the blind deconvolution, using an increasing number of modes, and we'll see how that helps the reconstruction. So this is the input data set here. This is a series of, this was a burst of 150 images that we looked at. And so this should be as well. And so you can see again how that seeing varies. So all the images, these images, and then the reconstructions we'll see have all been scaled to the same grayscale levels, going from about plus or minus 0.2. And so you see it's you don't see a lot of the fine structure here. But now when I do the blind deconvolution, and I try to fit those polynomials, I get, this is using 6 of those, so just the basic 6 modes. I get, already I've improved the image, and now you see the contrast is improved. You start to see the bright points in the middle of the field of view better.
Can you see once again the change?
Yeah. So that's the, so you see, yeah, and especially off at the edges too, the bright points are more visible. And then this was 36, so let's see, this was 6. I go to 36, to 105 modes, and even 300 Zernike modes.
So it's the same contrast. Right?
It's the same contrast. So, you know, the more modes you can use, it's more computationally intensive. Now I have to solve for 300 of those alpha coefficients. But if the seeing is good enough that you can actually resolve those, you're able to fit probably some more of the structure of the phases in the pupil.
Kevin,
Yes.
can I ask, you said this is a burst of images. How many images are there? And does that limit how many polynomials you can use? I mean, I would think after a while you don't have enough independent observations to warrant using 50 million.
50 million modes. There's probably, yes. You know, this was 150 images, so that, you know, does expand, you know, increase your ability to have a lot of modes. I don't know if it's, you know, if it's 1-to-1 for the number of images, the number of modes you can fit. I don't think it's quite that constrained, but you do have to worry about in these things overfitting, and, you know, you can keep throwing modes at it and it'll keep trying to fit them and get the image somehow sharper, but.
Yeah, I think it's definitely not 1-to-1, because if here you have what are your unknowns? Your unknowns are the 300 Zernike modes, right, and the values of intensity in the let's say million pixels.
Right.
And if you have 30 images, then you have basically 30 million equations.
Right.
Right, in the simplest way. But now, of course, they are all very degenerate to each other because a lot of them are very, very similar.
Right.
So I don't know, we should probably read the papers, but there are probably some numerical things that we need to think about.
Right. And as we'll see, it's actually not a million pixels because I don't do it on the whole field at once. So there's auto reduction. But yeah, taking care of, being careful not to overfit, and that, the normalization keeps you from, going down some minimization path that isn't realistic is important. But and there has been work on looking at the whether these are accurate reconstructions, and I'll show some of that later for the Speckle in particular. So that's great. We get this nice sharp image. I get 150 images. That's great. But there's also part of this is called the multi-object blind deconvolution. So that is an extension of this technique that makes it even more powerful for a lot of uses. And this is where, instead of just using a sequence of one sequence in one wavelength of 150 images, I can now include several different images taken simultaneously, strictly simultaneously, so they should be sampling the same phase errors. And then I take all those images together, and I can do this fitting for the phase errors for that whole set of images in multiple channels. And this is just an example of a schematic of a data set where you have this, on the top would be our white light broadband channel. We just have one, so there would just be one series on the top. In this case, they were talking about having a different diversity channel in the top, in addition, in the wideband. And then you have different wavelengths and different polarization states being sampled simultaneously. And so, and you see some of those different, the different polarization states, the left circular polarization, the right circular polarization, aren't all sampled during the entire sequence. They're just a subsample of the whole data set, but it's still able to connect all these together and use the information from all those channels to do the whole fitting. So, so what does this look like in practice? So here's a sequence now. We have a series of, this is the same series of 150 images. The white light image is on the right, or on the left, excuse me. But on the right, we have an IBIS, we have a narrowband channel scanning through the H-alpha line. And we have multiple images in each wavelength. And so as we step through, we see that white light channel staying, affected by the seeing, but the narrowband channel as well. And then we see the wavelength changing as we scan through on that narrowband channel. And so now, over this course of 10 seconds or so, we're tuning through the line profile, getting multiple samples at each wavelength, and then going all the way through the H-alpha line. And if you look closely, you see the seeing distortions are well correlated. The images are simultaneous. So the seeing, certainly the motions that you can see visibly, easily by eye, but also the other distortions are the same between the two channels. And so now you feed into, I have 150 white light broadband images on the left. I have 150 narrowband images, but with 10 images at each of the different H-alpha wavelengths. I feed that whole thing into the blind deconvolution software, and it takes those and reconstructs the final image. So there's the white light image we saw with the just a single one. It just takes all 150, collapses them down to a single, but it keeps all the, produces a separate deconvolution for each of the different wavelengths as it goes to the line profile. And so now this is the reconstructed. So now you see the image is sharper, it's much more stable. You can see how it scans through that line profile. The other thing, this technique, combining multiple images, getting out this reconstruction, it also improves your signal to noise, because now I'm combining the flux from those 10 different exposures in the narrowband channel into a single image, and it's sort of conserving the flux and adding that up in a smart way in Fourier space, so I'm able to maintain the resolution, but also reduce my signal to noise. So I increase my signal to noise, or to reduce the photon shot noise by adding up those multiple frames. So that's the blind deconvolution, and as I said, this takes about 10 seconds to scan through the line. We don't have the fastest camera in the world, but it points to a problem here. The sun won't stay still, right? You're trying to take its picture, and it's moving around, and it's evolving. So all this we were talking about assume that object from the sun is invariant, is the constant we're looking for, and we're trying to find just this time-varying MTF. But of course, whatever we're looking at on the sun is generally evolving. I mean, that's why we're looking at it, because we want to see how it's changing in most cases. So the question is, how fast can things change on the sun? And so for this depends, the speed at which things change depends on whatever propagation velocity, but how the changes we can resolve depends on how finely we're sampling the sun. So if we want to calculate in our image, how fast some change can happen on the scale of a pixel or 2 pixels due to some propagating error, we can just calculate and need the size of our pixel in kilometers, and then we just need to divide that by whatever speed we want to think a propagation, or whatever speed some propagating change in the solar atmosphere may have. So we can do a few calculations here and see how much time we would have to sample a line profile, or take a sample this burst and try to get a series of images in which we can assume that there's no changes in the in the original object. And so, some examples of some different pixel sizes we have is sometimes we have a half arc second pixel for HMI, so it's a nice big pixel. At the high resolutions, or now the moderate resolutions of things like IBIS, 0.1 arc second pixel, and now with DKIST we're going down to 0.02 arc second pixels. So of course that time is going to change. And the kind of speeds we have to worry about typically are the sound speeds, which range from 7 kilometers or so per second in the photosphere. 10 kilometers a second doesn't change too much as we go up to the chromosphere. But if we're thinking about alphane speeds now, if there's propagations on alphane timescales or magnetoacoustic timescales, those can be much faster than the acoustic speeds, so those are even higher. There's some debate about whether you need to look at the sound crossing time for a single pixel or your resolution element. But typically, that's within a factor of 2. So how much time do we have for these different things? Well, for an HMI pixel, looking in the photosphere, as long as they sample the line in 50 seconds, or so, there probably isn't much evolution due to acoustic propagation in their pixel. With something with a 0.1 arc second pixel, like IBIS, and that again in the photosphere, 7 kilometers a second, we have about 10 seconds where we can reasonably assume there's no change. But now as we go to something, go to DKIST, we have 0.02 arc seconds. Now the sound crossing time of our pixel is just 2 seconds. So now, we're going to start having to figure out just how much the changes, how those are going to affect our deconvolution or any of these reconstruction things that are based on assuming this time invariant object. And if we're talking about alphane propagation across a pixel, it's a fraction of a second. Yeah, we're not going to be able to get a whole sample of images on those time scales. I mean, we are running it, the cameras will run at 30 frames a second, perhaps. But, so yeah, this just shows this becomes an increasing problem as we go to higher resolution. We have to look more carefully at how to deal with this possibility the object is varying. All of this is just for an acoustic propagation or some kind of wave propagation where I'm seeing an actual change in the propagating across my pixel. There are, of course, with evanescent waves or you know, something like the P modes, they will cause variations across my pixel on much faster time scales. But I think we're lucky there in that their spatial scale and is much larger, and the time scale is a 5-minute P mode wave, so it doesn't really, the change is slow with regard to the sampling time we're using. No one ever talks about the effect of the, you know, that kind of change in you know, intensity where it's going much faster than the sound speed. But I think it's just because the spatial and temporal scales are larger than what we're trying to resolve. But if, you know, there are other cases where maybe it would be an issue. So that's just, you know, a warning and how we have to plan our observations, being careful in our sampling, getting enough temporal resolution. So the other technique I mentioned, so that was, it was blind, we talked about blind deconvolution, and the other technique was Speckle something, Spectral Reconstruction. There's a lot of terms that come after Speckle that I think I now understand what they are. So this is an example. It looks like the blind deconvolution. I have a time series of images there on the left, where I have, this is an image in H alpha, where I see the seeing effects, and I apply this technique, Speckle Reconstruction, and I get this nice sharp image on the right. So what are these Speckle techniques? Well, they're based on a couple ideas. One is that if you take short exposures, right, you're actually getting, you're preserving more information through your system, and your MTF has more high frequency power. So at the long exposure, MTF is that orange one, so you see it drops off rapidly, and towards high frequencies it gets quite low. That means you're losing all that spatial information. Whereas the blue one is an example of a short exposure MTF, and so you see there's more information preserved out to those higher frequencies because I'm not blurring all those out. I'm not mixing a lot of different PSFs that are varying with those time varying PSFs. If I mix those all together, they blur out all the high frequency power. So one single sort of PSF snapshot has these very, a lot of structure in it, but it preserves that high frequency power. Now the speckles are the different peaks of power in that PSF. It's no longer in any way sort of a regular, you know, axisymmetric sort of PSF now. It's got a lot of structure. And so Speckle techniques are trying to find ways to preserve that high frequency power and work with that, with these short exposures.
Okay. So when you're looking at this very, like this pattern, is like the smallest scale, the diffraction limit PSF?
Yes.
Okay.
Right. It's probably a lot of different diffraction patterns that are different parts of, whether it's the diffraction pattern of the full aperture or the diffraction pattern of your R0, it's probably more the diffraction, probably closer to the diffraction.
There's something in between.
Probably something in between.
I mean, this is very well defined, even
Right.
though it's completely random.
Right.
Still with this one, so if we knew this one perfectly, we could do probably a lot of good
You could-
things in
right.
deconvolution.
You can get that. Right. So yeah, I mean, yeah, it has a lot of that, all that high frequency power in there, and so the MTF is probably, this is sort of the radially averaged MTF on the left. Who knows what it looks like with the 2D case, but yeah.
You do it on subaperture scale, right?
Yes.
Okay.
So this has been used, this was used back in the 70s with film, where they said, okay, if you take short exposures, you preserve some more of the power than if you take long exposures. And so Jack Harvey and Breckenridge, they took exposures on film with exposure times of like 1 to 20 milliseconds, and then did the Fourier analysis on those film. And they claimed they said they could see a little bit extra power, the little parts of power out to 4 cycles per arc second when they did this. And so they were able to probe and look at what spatial frequencies were present in the granulation. They weren't able to do a reconstruction, right? You couldn't deal with any of the phases here just by looking at the power spectrum, but they could see where it was preserving that power at the higher frequencies. Just like that blue line, they could say, oh, there is power out there. It's just in a long exposure, it's blurred out. With the short exposures, we see it. And I like this because they have a little table in there, and they were able to determine which, up to what frequency, the cycles per arc second, they were able to detect some excess power, and they got down to about 2.7 cycles per arc second. So about 0.35 arc seconds. So there's still power, and there was theoretical reasons why there should be power at these frequencies. But now with DKIST, we're looking at 25 cycles per arc second. 50 years, we've gone up by an order of magnitude in our ability to diagnose the spatial scales of granulation. So just thought that was a nice leap in our spatial resolving power over since then. But like I said, just looking at the power, we aren't able to reconstruct the image itself. So how can we actually go about trying to reconstruct the image? Well, for that, we need to actually, for each image we get, we have to actually get determine what the PSF is so we can deconvolve it, right? So that technique that was just looking at the power was called Speckle interferometry. So they were just adding up these phases and getting the power. But what we want to do is Speckle deconvolution. And so this was developed a little later, and this is based on the idea we need to figure out what the PSF is, right? Just like we did for blind deconvolution, it was through this fitting process. But with Speckle, there's another way to do that. And so in any of these reconstruction techniques, we want to try to find, how much our power is reduced from the diffraction limited power spectrum, right? How much of that reduction in power in that short exposure, that blue line, is due to the atmosphere. And that's called the Speckle transfer function, just another way to, quantifying that reduction from the diffraction limited MTF to my seeing induced MTF. And so it turns out you have those two. You have the orange line there and the blue line, right? And the long exposure PSF falls off, and then the short exposure does as well. But how quickly those both fall off depends on the amount of turbulence in the atmosphere you're looking through. And there's a fairly well-defined relationship between those two as to the rate at which that power falls off in one with respect to the other, right? And how quickly, at what frequency they both fall off. And so back in the 80s, they came up with this technique that if it was very simple, if you just sort of took the FFT of the average, where you average the power of the FFT, right, that gave you sort of the long exposure PSF, right? You just take a bunch of images, you average them up, that's like you just took one long exposure, and you can find out what the MTF is of that long exposure. But if I take each individual image, Fourier transform that, calculate its power, and then average up the power spectrum, then I'm getting something closer to sort of the average blue line for that sequence of images. And so in that case, I sort of have I have a measure for the long exposure MTF, and I have a measure for the short exposure MTF. And I can try to use now what my knowledge of the turbulence in the atmosphere to try to figure out what the PSF should be, right? So I can figure out what R0 is, calculate a relationship between those two for different values of the R0, or the atmospheric turbulence. So I say, okay, now I know what the distribution of turbulence is in my atmosphere. I generate a PSF based on that, and I can deconvolve that. I get my Speckle transfer function, and I amplify the power at different frequencies. And so, this is the approach here. You get what are called spectral ratios. So it's just the ratio of the long exposure and the short exposure MTF. So you see at low frequencies, low spatial frequencies, they're the same. There's no real change. Short exposure and long exposure MTF. But then the ratio increases here as I go to higher frequencies. And so they all start there at 1, and they fall off at greater and greater spatial frequencies as the seeing gets better. Yep.
So we get this plot that you are showing now from like a simulated.
This, well, at the time it was all atmospheric theory.
So Kolmogorov stuff and so on.
And it still is. I think it's all freed and, you know.
So
it's all the theoretical, and you have to make. There's a series of assumptions in there about the atmosphere.
Okay, but this comes for, I mean, in practical terms, this comes, for example, from this code that, for example, Jose uses to simulate effects of the atmosphere on DKIST observation and behavior of AO and so on.
I don't know if anyone has actually used a whole atmospheric simulation to calculate this, or they're still relying on the more analytical model of the atmosphere. Someone might have, but yeah.
No, but in
theory, it's yes.
Yeah.
You look over you have a series of phases. You know, you have your turbulent simulation one way or another, and you calculate the phases, and you see how they affect.
Yeah, I mean, this was my question. This is a graph from the synthesized.
This is a graph from the synthesized, right? And so, and it depends on your aperture. How many of these different pockets of turbulence you have, right? The R0, as it gets smaller, you have more. You're averaging over more of these different turbulent cells over your aperture. So your seeing will get worse. And so, it goes from 0.5 up there down to 0.05. And this, I think, maybe this plot here, something like this, is why people also thought, well, DKIST will be terrible, because R0 is going to be much smaller than even if it's 20 centimeters or 30 centimeters, which is great if you have a 1 meter telescope and you have, that's a 0.3. Now with a 4 meter telescope, now it's down at 0.05 or whatever, right? You're getting this. If you just think that R0 over D is what quantifies your seeing, then you have this effect. Luckily, it turns out that's not. In simulations of Jose, showed that it's more complex than that. So yeah, these are just a series of plots from simulated atmospheres. And so the idea is, well, I can look at these, compare these to my observations, and see what happens. So I went back to that burst of images we had, 150 images. I calculated along the average, the red line, the FFT of the average image, and then the blue line was the average of the FFTs of the individual images. And so now I see, what do I see here? Why is the blue line flattening out there? And the red one keeps going down?
You lose the high frequencies.
Well, it should lose the high frequencies in both. But last week, when we talked about that, yeah, so it's the average of 150 images has very low noise, right? I've averaged out a lot of photons. My shot noise is very small. But each individual image still has an amount of noise. And so it's sort of the average of those individual FFTs level out. And so when you do this, in the proper Speckle code, you need to sort of have an estimate of the noise, and you can apply a correction there. But yeah, it shows much like, at least down to some spatial frequencies there. You see where the two correspond very nicely at low spatial frequencies and then start to diverge. So I can do that spectral ratio. And then this is my plot here. I see where they're sort of similar, and then they fall off in frequency, as we saw before. And so that looks, from this, using that model, I can go and figure out what my R0 was for these observations. By the power of PowerPoint, I can overlay the two on top of each other here. So the orange line is the one I just showed you there, the spectral ratio that I measured, and I've overlaid it on these old curves. And you see it does sort of show, they don't line up perfectly, right? There's a lot of, there's a few reasons for that. But they are sort of close, and if I had to pick one of these curves that I was following, sort of maybe the circles there, probably the closest triangle. So I go over there and I say, well, the circles R0 over D was about 0.3. This was at the Dunn. I had a 76 centimeter aperture, so my R0 is around 25 centimeters. So pretty good seeing. It was good seeing. That's why I could fit 300 modes probably to these data, when normally you can't do that. But it gives me an estimate now. Now I can apply the simple analytical formula to calculate what the PSF is for that R0. Basically, the R0 tells me what sort of the structure, the average phase structure is across my aperture, right? If I have these, the number of different cells I have across my aperture of my telescope with different phases, I can sort of get a distribution of phases, which will give me the PSF and the MTF that I can now deconvolve my data. So does this, to some extent, this is a little wonky to me. This is like fitting these things to these curves that are calculated through a lot of approximations about the atmospheric structure and so on. And those, how you actually choose which curve you're fitting, since they don't always line up. But this has actually been, yeah.
Well, how exactly do you get the PSF out?
From this?
Yeah.
Well, you get it out just by, if you know R0,
yeah,
right? That will tell you the sort of the spatial scales and of the structure in your atmosphere, and you can calculate an average PSF for an atmosphere with that distribution of turbulence.
And you apply the average PSF to the average image.
And you apply the average PSF to each image, to each of the images in the burst, right? Sometimes you may be overcorrecting and undercorrecting, but then you average them up and you get out the reconstructed image. But yeah, you apply it, you're getting the short exposure MTF, and you're applying the short exposure MTF, the approximation here, to the short exposure MTF to each image, each short exposure image, because that's where you still have the high frequency power, right?
But when you transform the image in the Fourier space, you have phases as well. And from here, what it seems like you're doing is just you're looking at the power.
With this, well, this also gives you the phases across your aperture, for a distribution of phases. Yeah, I think the STF has. I think it has information on the phase correction as well. It gives you a complex MTF that you apply. So so this, how do we test this to see if this actually works? So we did a test back 2008, shortly after Hinode was launched, where we took images from the Dunn the same time as Hinode was observing. So Dunn's a 76 centimeter telescope, Hinode's 50 centimeters, so similar in size. Applied the Speckle reconstruction to the two, and they both came out pretty similarly, right? They look like we're not adding a lot of structure, or we're missing a lot of things in the reconstructed image. So that's good. We can look at that more quantitatively here by looking actually at the distribution of power in these images. So my average image from the ground-based data is that red line. So you see the long exposure MTF effect there, so it drops off in power. Take that burst of images, apply the Speckle reconstruction. It takes out the atmosphere and the aperture as well. It deconvolves for the combination if you provided it knows the aperture of your telescope, so it deconvolves for the whole thing. And so you get that black line, the Speckle reconstructed image. And the green line is the Hinode power spectrum. So we need to take our Speckle reconstructed image for the Dunn and apply the Hinode MTF to it. We looked at how they got the Hinode MTF last week. So we convolve our image from the Dunn, our Speckle reconstructed image from the Dunn with the Hinode MTF, and we get that blue line, and the two of them line up very nicely. So we're adding power, we're correcting for power over that whole broad range of frequencies fairly accurately. So, that gives good confidence that this is, photometrically, it's correct across this range of frequencies in this case. So, now one thing about Speckle is I'm doing this statistical process where I'm comparing my long exposure MTF and with the series I get from a set of images. And so as you see, there's this 1/n here, right? So I'm adding up a series of n images, and I used 150 there before. And so you do need some number of images, in order to get good statistics and get that the spectral ratio curve. So I tried using that same data set and taking subsets of smaller subsets of images, what happens to my spectral ratio curve. So if I just take 50 images, well, the blue line is under there, that's still the original spectral ratio curve, and this is the 3 gray lines are the 3 different blocks of 50 images. And you see they all still lie pretty closely, one on top of the other. But if I go down and I just take 10 images, right now any one of those realizations of my spectral ratio curve from just 10 images now shows a lot more variation. And as I go now fit to the theoretical curves there'll be some error in that. And so that's why with Speckle, you're doing the statistical process. You need some number of images in order to get a good sample and get good statistics when you take the ratio of those two MTFs. This is somewhat cheating. I was using the whole image here, and so my noise is going to be lower significantly because I have this 1,000,000 pixels across my image. As we'll see, I don't always get to use 1,000,000 pixels, so then having a smaller number of samples means this noise will be larger. But it does indicate why, with Speckle, you need a fairly large number of images. Typically, 80 will be the standard for DKIST, 100. We heard a couple weeks ago at the Big Bear, they use many fewer than that, and it still seems to work. So they used about 20 or 25. Still works with 10. I've done it with 10. So it depends. Yeah.
So,
Whether it's photometrically as accurate, I don't know. But.
So out of these 150 images, typically you get one average spectral reconstructed image.
Right. Mm-hmm. Okay. Right. So then you would get one image out, and yeah. So we saw how the blind deconvolution was set up to use multiple different channels, and it would do this. It would solve that whole set of equations for multiple channels at the same time, and use all that information in the minimization process. Theoretically, that's possible with spectral reconstruction as well, and as well as using information from the individual images to try to recover the PSF for a subset of images in the burst, like so you're doing these wavelength bursts at each wavelength and reconstructing those separately. And there has been some proof of concept of that as a method. It hasn't certainly been as tested or applied in solar physics, but theoretically it's a similar process and it should be possible. One issue with that is that you're just getting enough as you go to fewer images, you may have a moment when you have a bit of bad seeing, right? Or the seeing is worse in one subset of images than another. And then you just have lost all that high frequency power. And even if you know the PSF and you try to, you can't recover if that power is all then lost by a wide, each of those short bursts, each of the short images doesn't have that power. There's no way to recover it. So now one problem, one issue that's been addressed with Speckle is that it's using a statistical calculation. It should, here's what a turbulent atmosphere looks like. Here's what the MTF should look like for a turbulent atmosphere, and applies that. But now, that was all developed pre-AO, and so now when you use adaptive optics, you're actually not looking through just a simple Kolmogorov atmosphere anymore. You're correcting some of that turbulence, and the accuracy of your correction with AO for that turbulence is better on some spatial scales than other spatial scales on your pupil, right? You can correct certain modes, like those Wernicke modes across your pupil very well, but other ones AO isn't is able to correct as well. So you see on the right there, that's what happens if you don't have AO. You see that both the short exposure and long exposure MTF drop off very rapidly. So I do want to, you do want to use AO, and then that increases that will change your long and short exposure MTF. And when you do those spectral ratios, you have to take that into account and apply that model of your adaptive optics, how it's correcting, and put that in order to properly recover the Speckle transfer function, that correction for your AO. Now the issue is, as we said, the AO is correcting. Yeah.
DKIST is going to be the first solar telescope using AO, or there are others?
Well, we already, right, there's other telescopes use AO, and there's the correction for the adaptive optics in the Speckle reconstruction process is well established. So the DST, for example, there's a model of the AO. Speckle, the Speckle code has a model of how the AO works and is applied in there. So,
but DKIST will be the first with MCAO once they have it, right?
Well, Big Bear.
Big Bear. Okay.
DKIST will be the first. So all of this process of doing the Spectral Ratio to try to figure out what R0 is, right? This is this whole process that uses all the statistical measures and so on. It will be possible from DKIST. The AO will actually spit out an R0 number. As it's measuring these different phases, it'll be able to calculate some R0, ensemble R0 for the atmosphere at each given instance. And that will actually be fed into the Speckle. So Speckle will have a starting point, certainly, or it will rely on that R0, the actual measured R0, in order to do the reconstruction, and won't need to rely so much on that Spectral Ratio method. So hopefully that makes it more reliable in terms of doing the reconstruction.
And the R0 is measured over what kind of interval?
For the DKIST,
yeah.
I mean, the AO runs at 2000 Hertz.
Right.
I think it spits out an average R0 for your integration time.
But that will be different for different instruments.
Sure, each instrument might have,
Right.
I don't know whether it puts that in real time, in which case it would be more, or it goes back later and looks at some, does the average over the proper interval. But there's also the problem that AO works differently in different parts of the field of view, right? I mean, there's, people see that now, AO doesn't correct the whole field of view, that's why we need MCAO, and the fall off on its correction, how well it corrects, depends both on the AO performance, but also on the specific seeing conditions. So you need to, this is why you need to do this whole model of the AO, not just to look at its correction on the lock point, but as you move away from the lock point. So the black line would be the AO, this STF magnitude of the correction at the lock point, I think the dark black line, and then as you move away from the lock point, that STF changes. So you have to, across your field of view, apply a slightly different correction to get the R0. So started talking there about different parts of the field of view and AO and stuff. So what is the problem that we're facing here? Why is different parts of the field of view have different seeing? We're looking through the same atmosphere. Well, we saw this before where we had, here's the plane wave coming through these different bubbles of the atmosphere. But now if I look off away from that one point, now my line of sight is going through slightly different parts of the atmosphere. And I'm seeing different turbulence, different index of refraction changes along my line of sight. This gets worse as you see in the lower level, sort of the ground layer. That small change in angle, because that turbulence is so close, isn't as important. So the ground layer seeing is more constant over the field of view. But it's the high altitude seeing where just that small angular deviation, right, ends up you're tens of meters away up in the upper atmosphere. So now you're looking through some completely different bubble and change in the index of refraction. So the term we use for this is what's called the isoclimatic patch. So it's the size of some part of your field of view where the seeing remains mostly constant, right? And then as you move away, it changes. So a big isoclimatic patch, if I have 10 arc seconds where my seeing remains constant, that means I'm much more able to correct over the field of view. Generally means the seeing is better over the entire field of view. So yeah, here there's even other things I'm going through. MCAO will help by being able to measure those different layers of the atmosphere and what the actual turbulence is. So here's just an example over the space of an observation. On the left, I have a very small isoclimatic patch, right? My AO lock point is somewhere there where that sunspot is, and right there in that box, it's nice and sharp. But then as soon as I get outside of that, AO has, what it's correcting for is in no way correlated with the atmosphere that other parts of the image are going through. And so it looks washed out, may even be making it worse as you go away, the adaptive optics corrections. But sometimes, right, I have a nice sharp field of view in the center, sharp image in the center, but I maintain that the quality of the image over the entire field of view. And so, that's an indication of a different kind of seeing. So, how do we deal with this in all our reconstructions? We alluded to this, that instead of, so I can measure the R0 in one area, right, where I have an isoclimatic patch, I can isolate that area, I can calculate my Speckle ratio there, I can just do the Fourier calculation over some subfield and get estimate my R0 in that subfield. Or I can do the blind deconvolution, the same thing. I take out just an area that I assume has the same seeing conditions, apply my technique on that subfield, and then parcel up my whole image into a bunch of subfields where I assume each subfield has the same seeing, and do these techniques on small subfields of the images. And then afterwards, I go back and I combine all these subfields, corrected subfields into a full image. In practice, all these subfields are overlapping by half, so I'm sort of able to merge them together smoothly and get these nice smooth images. And you saw that in all those, the MFPD, the blind deconvolution, and Speckle, those were all done on subfields.
How do you choose the subfield?
Well, you don't have a lot of options. You like to be a power of 2 for your Fourier transform. With our current resolution, the isoclimatic patch is never huge typically on our current telescopes. So really you want a subfield that's on order of a few arc seconds. Right? So if the seeing's pretty bad, it may be as small as 2 arc seconds if you have, so you have 32 or 64 pixels or so across your image, across your subfield. But you're usually never going much bigger than that, maybe 128 pixels. Again, with DKIST, I don't know. You may have more freedom because some of the problem is you can't go to certain subfields, smaller subfields. You just don't have. You're doing Fourier transform 16 by 16 pixels. You're not going to get very much signal noise in order to do either of the techniques. So yeah, I don't know if we can now if we have 100 pixels per arc second or 64 pixels per arc second. Can we do these reconstructions with DKIST on arc second scales? Whether that helps at all or not. Again, it depends a lot on the atmosphere. The one thing that's different about DKIST as well, I'll mention that, the high altitude seeing is much better because it's below the jet stream. Almost every other observatory, whether it's the ones in the US, the Canaries, they're all influenced by the jet stream going around. But because it's a little bit further south, the jet stream is almost non-existent over Hawaii.
What's a jet stream?
So the jet stream are these big global currents that go around, and sometimes they move around, and sometimes they're over the ground-based observatories, sometimes they're not. But they're almost all stay north of they're above the tropics. In some sense, the tropics are where you don't have the jet stream, and so a lot of the high altitude seeing, which is the more problematic for this isoclimatic patch, that's where the effect of these small deviations, which is a much different piece of atmosphere, and they're moving very fast. If you're looking through the jet stream and these pockets are moving along at 100 kilometers an hour, your time variations are too fast for AO to really keep up with. So, that we could be in a whole sort of very different seeing regime with DKIST in some sense. So yeah.
So going back to that photo, will DKIST make its own subfields, identify the R0 for each subfield?
So yeah. So when you're doing the Speckle, right, you would cut up the subfield, you would calculate the average of image for that subfield and its Fourier transform, and then calculate the Fourier transform for each realization, each image in that subfield, and then average up those. So yeah, you would be doing the calculations within all that Fourier transform would be one subfield at a time. How, with DKIST, with the automated Speckle processing, how it determines the size of that subfield and so on, I don't know how that's optimized.
So these subfields also have to be the right size such that the seeing is not super clear on the bottom left and crappy at the top right.
Of the subfield?
Yeah.
Yeah, I mean normally you choose a size for the subfield. It should be a little smaller than the isoclimatic patch so that you don't get a lot of variation within the subfield. Yeah, and again, it's always that balance between getting it small enough that you sort of have a constant seeing, but not so small that you don't have any signal to actually to work with. So, now a question. So what's the most famous Speckle reconstructed image in the world?
Solar physics or general?
General, in the world.
Speckle. Some military thing.
Speckle is used for military. It's somewhat worrisome.
We don't know about that.
We develop these techniques, and then you go and look, and there's articles about how they use Speckle reconstruction for looking at horizontal imaging and trying to measure things as far away through the atmosphere so they can see.
It's something
Better targeting.
Something in the lab, some bacteria or something like that.
Oh my, is this one?
I was about to say.
Certainly
Although
today
it is still on the New York Times now, though.
it's a fair,
Oh, is it?
certainly the most famous Speckle image today. So yeah, so these were all processed with Spectral Reconstruction, and I don't know what the subfield was. I looked at the contrast across the field of view, and it's fairly constant. Right? So there is perhaps some, as that speckle, as you move away from the lock point, maybe your speckle isn't working quite as well. Again, as you saw, you need to tune it for the AO you have, how well the AO is working, and it also depends on the atmosphere to some extent. So, so yeah, there's probably work in tuning the speckle, but it looks pretty good. So this is the image we saw last week, the Reardon image, and that's the DKIST image. I labeled them for you. So,
So you're pulling a Matthias on that.
like I said, he is his own elaborate prank by Matthias Rempel.
yeah, so get that. Look at that zoomed in one from. Oh no, wait. Oh, that's backwards.
Yeah,
That's
backwards.
There isn't enough field in Matthias' simulation.
Right. So yeah, this is backwards.
Which ones are different?
The one on the left is the Bureau. I mean, it actually, yeah. It
You put it on purpose so that you would
I know.
that you'll
See
be
if I
fooled,
can-
right?
Yeah, the bright points do look different.
They do. And I'm seeking them.
They're fatter.
Which ones are fatter?
Well,
The ones
all these
in
here
real life.
are quite. They fill the. In many cases, they sort of fill the intergranular lanes. Whereas here, they're all.
Well, I guess it depends what kind of organic field we put
Sure.
into the simulation, right?
Sure.
But that's the other thing. We have to find the scale because those granules are larger than these granules.
So yeah, this is a.
We have to
So I was
fix
trying to. I wanted to get to magnetic field. I tried to wanted to line it up with HMI. But so I went and looked. We've been doing power spectrum. So let's do a Fourier power spectrum of the image. See what power and frequencies we have here. So this is the Reardon power spectrum. Falls off high frequencies. And so this is the, now the red is the power spectrum of the DKIST image.
Oh my god.
And they don't line up at the low frequencies. Now the high frequencies I could, that's a lot of the physics under there and no one's been able to test it and see. But I would have thought at the low frequencies, arc second scales, those should line up better than that. Yeah.
Sorry, I have a very stupid question. Why is there not a bump in this power spectra when we obviously have the granular scale as an important scale? Like when you do the power spectra of cosmological stuff, you see typical like sizes of distances between galaxy clusters and so on and so on. And here you just see this falling off.
Well,
What am I missing here?
well,
Or is there actually a bump at the beginning?
might be a bump.
It would be at like.
this is one
Oh,
arc second.
It would be at like one
This would be like 2
or
arc seconds is that first tick mark. So 2 arc seconds.
Okay,
is
so
sort of-
it's actually there.
it might be
Yeah.
buried up there.
Okay.
On the other hand, there isn't a super obvious spatial scale. That's maybe a broad sort of bump, right? They're in a variety of scales. There should be some sort of bump, but maybe not
Okay.
at a super
Maybe not on
specific,
point. Okay.
specific frequency. But yeah, it's kind of lost. We're out here on this scale. I'm going out to less than 1/10 of an arc second. So yeah, I mean, one way I can correct this is just by assuming the spatial scale is wrong. D is I don't know. It falls pretty nicely on here.
0.25 arcsec minus 1, right?
All the way to about
4.
4.
So it's
0.25 arcs.
that's
So-
a big change. 8 out of 40, that's 20% change.
I don't.
I don't know.
Did you convolve the mirror simulation with the DKIST PSF?
I think it already was involved.
Because if you do this, you're gonna drive down the power in the high frequencies, and you're gonna drive up the power in the low frequencies.
Are you gonna drive up the power?
It must just mix the power somewhere. Yeah,
Well, another
I
thing
thought this
is,
was already, I understood, and I got it from, I thought it was already involved. It's
another thing that
diffraction limited.
might trick you is that those best famous whatever images, they're not linear. That's not intensity. It's some sort of beautiful image scale that makes it great on the New York Times, but I don't know that you have any linear, relationship with the actual intensities, and I don't know how much that is gonna kill or change or trick your power spectrum.
Yeah. Yeah, there's certainly. You would think the low frequencies, though, wouldn't be too affected.
Sure. Yeah. But I don't know.
You mean there is like a
I
gamma?
mean, if you really want to do it, go to Friedrich and get the actual original images then, rather than what they have done in the lab, media lab.
What do people online think of the images?
Is that people like?
Any questions?
They did that on.
Anybody awake?
Yeah, actually, I was doing the numbers yesterday. Is that true? That one SD HMI pixel, there's about 900 of these pixels?
So it's 0.5.
It's 0.5 versus 0.015, 0.2.
Right. 0.02, it would be
Between
625.
Right.
Yeah. So yeah, one HMI. So this
One
is.
HMI pixel covers the
So
same.
this square is 12 megameters.
No, but one is the HMI is 0.5, and the Friedrich told me is 0.015.
Right.
So it's 300.
No, it's 39. 30 square.
30, yeah, that is right. Sorry, 900. Yeah.
So I was.
Pretty good.
Okay.
So yeah, this is 12. This is 12 megameters, and HMI pixel is 360 megameters.
HMI pixel?
360 kilometers.
Yeah.
So that's 10,
It's 3
30,
times 12, 36.
so it'd be 36 by 36 pixels.
I
Whereas
don't know how
this
you can do your remapping. It's going to be interesting.
would be a blob of pixels.
I have like a sort of question just to see if I understood everything. So the main difference between MonthBD and Speckle is that MonthBD actually fits for the phase distortion, so to speak, approximately using Zernike polynomials. While the Speckle somehow statistically makes use of the relationship between the instantaneous and mean or average MPF of the atmosphere, right? And now you have two questions related to that.
It's still using, I didn't mention, it still uses the polynomial representation of the phase errors. It expands, based on that R0, it expands to a certain number of polynomials to represent the phase errors. But yes, it goes about finding what the coefficients are very differently.
Okay, but now I have actually three sub-questions. One sub-question is, can we also get, like for example, one of the good things of MonthBD, which maybe we won't be able to use with DKIST now, but we will in future, is that you can use these Zernike polynomials to convolve other data, like for example, spectrograph data that was taken simultaneously with your images.
Right.
Do you also get that sort of information from the Speckle or no?
I don't know if it outputs. You should be able to get, right? That's telling you the PSF at that in that subfield at that time. I mean, it should be, and it drives that from a series of phases, so it should be. You should be able to get that.
Okay. The other question is, so the Speckle also somehow, does it assume that our R0 is constant over this observation period, right?
Over the subfield.
Over the subfield and also over the time when we took the images.
When you
Yes,
use your burst.
yes, your burst. Yes.
Yeah, when I use my burst. So what would happen if we departed from that? Would we get like worse images, or we would get some complete nonsense?
If the R0 is varying, I mean, I don't know whether it would give you the average R0, right? You would get some estimate that's sort of somewhere in the middle of your range of R0, and then you would apply that. It works usually, and R0 must not be constant. You could see it in that 2-second image. So I think it still would give you a good image, but I'm sure there are cases where it might fail in that. Depending on how,
Okay, and the last question is that I know that, for example, MongoDB codes are like super cumbersome and hard to use and super parallel, and you need to like sell your soul to whoever in order to be able to use them properly. What's the situation with the Speckle? Like you now showed us very super beautifully how the things work. So how hard would it be for a random person from this room to sit down and devote some time and write a Speckle code?
Had to write a Speckle code?
Yeah.
Yeah.
Like even the most basic one.
The most basic one, right, is pretty, you use the spectral ratio in your subfield, you have some lookup table for what your R0 that is, and then you have to compute what that phase function is across your pupil. It gets into atmospheric theory in there. So that probably be the hardest part. So yeah, Speckle has the advantage because it's not solving this system of equations. It's much faster, right? You run through each image in the subfield, you do this Fourier transform, you get your thing, and then that allows you to calculate this, the PSF. So it's very fast compared to the blind deconvolution, which as you add modes, as you add more images, you're now just solving these bigger and bigger systems of equations. So, you definitely, there's a computational cost in that. But arguably, especially for this multi-channel data, it's given the best results in combining, a lot of data sets. So.
I'm asking the question because nobody here is probably, also it also counts people from the online, not everybody here is like interested in 3D modeling or diagnostics or so. Maybe some people are interested in this and maybe want to try themselves. So maybe in the same way that we're going to write like a weak field approximation inverter or a Milne-Eddington inverter or something like that, maybe people also can try, not necessarily for the grade, and maybe not everybody, but would it be possible for people to try on their own to write the code just to gain more insight into this?
Sure. Yeah. So.
That's a part of the class.
Well, as a part of extracurricular activities.
I understand.
We're not going to force anybody to write a Speckle code. A few days is okay.
A few days would be okay, but I don't think it's going to be.
You don't think it's going to be good?
The theory is all from the 80s, right? So,
should be learned by now.
so it could make it easier, it could make it harder. You have to go back and figure out what Fried and Rallier were thinking. So, But yeah, to some degree, it's a fairly straightforward process. It'd be interesting to calculate look at those speckle ratios that come out of the simulations, see how those correspond to the analytical sort of approach to those, since, especially for specific atmosphere or whatever, it could be different.
So I have a question. If we have this very thorough understanding of our system, like of the optimal optics and the atmosphere of it, why do we compare a simulation convolved with just a single PSF with something spectral reconstructed instead of convolving our simulation with a systems model and then reconstructing it with the same speckle code and then comparing the two? Because right now we're not comparing apples to apples.
Right.
I mean, it's easier. Yeah.
When we understand our system and then we understand we have this aperture and we have this adaptive optics that works like this, what we don't, there's no way to put in that system's, the atmosphere that's going through a specific image, that the image, specific part of the image is traversing at a specific time.
Mm-hmm.
So yeah, you could, if you're saying do it on a statistical basis, generate a data set of blurry simulations to compare your, people want to look at nice images. I'm not sure fundamentally it's different. If I understand my atmosphere enough that I could put it in a systems model to apply to the simulation, I must. Sure. It's easier to compare data sets, I think, if you remove some of the effects. Yeah. Blurry image on the cover more times. They're going to use it for statistical evaluation.
But so in theory, if everything works perfectly, the speckle should also remove some of the diffraction PSF.
Right. So it also includes the aperture PSF.
So why do you involve the DKIST with the Reardon with the aperture then? Should you just compare the simulation with the Spectral Reconstructed?
Well, you're still truncating those frequencies, right? Even if I deconvolve to get back to the theoretical diffraction limited MTF, it's still falling off, right?
But the Spectral is like slightly better than diffraction limited, right?
Where do we have? There. So yeah, that Spectral Reconstruction should be what you would get through a diffraction limited system. Was it I'm taking out the whole MTF?
Why should it take out?
Because how does it know the difference between the atmosphere and the aperture?
Well,
it's deconvolving the atmosphere PSF and the telescope PSF.
Right.
But that doesn't just invent all of the frequencies that are beyond your diffraction limit, which are present in the simulation, but not in the observations. Like deconvolution can't take a zero and make it something non-zero.
Because at some point you're multiplying with zero. You will see.
You get a zero divided by zero, which is undefined.
Makes sense.
Okay, we are a little bit off our time, which is actually great because it's always nice to discuss. So let's thank Kevin. Next week we are going